So, hello everyone. We can start the session now. Good morning, everyone. I am Hemantam. I am a coordinator at Mathematics Club IITM. So, this is your last and final session of Summer School 2025. This is going to be on functions that can approximate the universe. So, as you all know, AI has impacted every bit of our life. It is changing the way we think, the way we access information, and so on. It is changing every aspect of our life. So, but the unfortunate thing is that the heart of AI, that is the mathematics that has enabled it, has been black boxed by its name. Meaning, most of the people know about AI, like they just know the word or use it, but they exactly don't know how it works. So, the aim of this session is to unbox this black box and to unreveal the mysteries behind it, or what may first seem to be as magic won't seem as magic by the end of the session. So, let's start. So by the end of this, well, first go over the agenda of this session and then continue with the main details. By the end of the session, AI will no more be a buzzword or a magic. You will be able to make more sense of this figure, meaning for now it just looks like two circles or some Venn diagram kind of thing. You'll appreciate this figure much more by the end of this session. And in this session, you'll also see how neural networks can approximate any continuous function as well. So say like this, it's trying to approximate this sin x function here. Here it's trying to approximate some random function here. And you'll see what are the different ways of doing this, what happens if I increase the number of neurons, and so on and so forth. So first I'll be showing you what all we'll do in this session, and just to make you curious and hope wait for what will come next. And now I'll want to take you over to this. This is one neural network playground. Uh, can you see this thing? Huh. So now here, this is a neural network playground developed by TensorFlow. Here, like it's a very nice thing. Like you can add more layers, you can add more neurons, you can even customize the activation function that you want. You can customize everything. Like you can change the data set, everything. You can change ratio of training to testing data. And then when you when you click on train, it will show you how this classification boundary will change as time as training evolves. You can even see what each neuron has learned. So basically why I wanted to show you is, if you got what I wanted to convey here, it's a good start. Even if you didn't get anything that I said, it is still good, because by the end of the session you'll make more sense of this. So after this session, I hope you go, visit this site and just play around, tinker around all this by changing whatever you want, and see how training network actually works. So I just wanted to show this in the start to make you guys curious what are the aim of the session. By this end of the session, you will appreciate this much more. So now coming back. There's also an hands-on origami demo. I mean, it's not exactly origami, but like it is just to illustrate a beautiful concept that is related to this. This will also come in the later half of the session, where you'll see that just folding a paper can help you understand one different an idea here. And so let's begin. This was just a brief intro of what all will happen in the session to make you guys curious. And now let's begin. And before we begin, like I want you all to put your attendance in the chat. This will be the first round of attendance. So I'll wait for a minute. So hope you all have put your attendance in the chat. I'll continue further. So what is this session all about? What are we trying to discuss here? So it's all about the human brain, meaning people have been trying to understand how the human brain functions, how is it capable of doing all different things that it is doing, and to try to mimic the human brain from from ages. Now, one thing, if you go and study how people have approached this thing, one thing that you notice in common is the quest for building a mathematical model of the human brain. So why do we need a mathematical model? It is because if we have a mathematical model, then we exactly know how it works. And apart from that, even if we have such a precise model, then we can even implement it on a machine and simulate what is known as an artificial brain. So, this idea of trying to mimic the human brain has led to the evolution of all these fields that we hear today, like machine learning, artificial intelligence, and deep learning. So, this session is going to revolve around trying to build such a mathematical model of the human brain. This is a high level overview of this session. So let's first start off by discussing the roadmap. So first I'll show you what all topics, how this session is structured. So firstly, we'll go over some early models of human cognition, meaning how people tried to answer this such questions about human brain long ago. Then we'll move on to connectionist machines. Here we'll discuss how interconnected neurons can build different complex systems. Then we'll move on to perceptrons. This was a remarkable milestone in this journey because this idea is still used even today. So even today, most of the neural networks, those neurons are basically perceptrons with some slight modifications. So this was a major breakthrough in this journey, and then we take over the ideas from connectionist machines and then try that on perceptrons by interconnecting them to get what is known as a multi-layer perceptron, and then we'll see how powerful this multi-layer perceptron is. Like I'll go over, I'll explain like three different things, meaning it's a universal Boolean function, universal classifier, and it's a universal function approximator as well. So this is the heart of universal approximation theorem, meaning the UAT that is written here stands for universal approximation theorem, which proved the power, this power of multi-layer perceptrons, and also showed why using a neural network can help us learn any kind of function. So you can approximate any function in this universe. So that was the reason why I kept that title. And then we'll proceed to neural networks, and then we'll also discuss some the basics of how a neural network is trained and all. And finally, we'll conclude by showing some the recent advancements in different mathematical modeling. I won't go into much of depth of that, but I'll just give you a glimpse of what all has come in the recent years. So let's first start by asking the question, what all your human brain can do. If you try to think about this, your brain can do a lot of things. It can see, it can think, read, write. Every single action that you can perform is given by your brain. But let's try to group this or categorize this into three major things. The first one is your brain can learn. The second is your brain can think. And the third is your brain can remember. So these are the three most important thing, at least for us to try to mimic in an artificial system. So let's first start by remembering. So how can we make a computer or some artificial inanimate thing to remember? So this gave rise to the concept of computer memory, and people have invented several different technologies over the past decades to solve this problem. So like in the 1940s, vacuum tubes were invented. Then in 1950s, magnetic drum memory came. Then latches and flip-flops, followed by hard disk, floppy disks, RAM, flash memory, and so on, like SSD and all. So just imagine, like a few centuries before, it was difficult for people to even just store a single bit. Like it was even difficult for them to imagine that we can store, make an artificial system to store information. And now today we are in an age where my laptop can store 1 terabyte of information, and even all of your laptops, phones, and all has so many gigabytes of information capacity to store. So it's a remarkable journey, and we'll not go over into much depth of this. So our main focus will be on learning and thinking, and that too mostly thinking. And these are difficult to model and simulate. And the reason is, if you want to store some artificial memory, It is basically, the idea is you want to make a system that is isolated from its surroundings, meaning uh, only you can interact with it whenever you want and change the information stored in that. The rest of the time it should be isolated. So that is kind of what they achieved using all these techniques. And the other two are revolve around this mathematical modeling, which is quite difficult to come up with. So now let's see about learning. So here, several different learning algorithms came up. Like in 1952, Donald Hebb proposed Hebbian learning. In 1958, perceptron learning rule came. And then in 1986, the most important learning algorithm till now, that is backpropagation, came up. It was proposed by many people, including Jeffrey Hinton. And this was a very remarkable milestone, meaning like even today all the AI models are trained using backpropagation or some of its variants. So this was the most important thing, and we'll discuss this in quite detail by the end of this session. And then comes thinking. So now we want to make a machine to think like us. Now, how do we do that? So people have been trying to attempt this challenge by from several ages, and we'll start off with some early models. And as discussed in the roadmap, it mostly follows how it works. Then we'll go over connectionist models, thinking gates, perceptrons, and so on. So, and our main focus will be on this section, meaning on thinking gates, perceptrons, MLPs, and neural networks. In the end, I'll just show you one transformer architecture, but I won't go into much detail of it. It's quite complicated. So now, first let's ask a question. Why is it so difficult to model the human brain? Like, why are we so discussing is this in such huge bit of detail? Is it so difficult? And the answer is yes. That is because this one simple circuit or one simple thing can do so many different unrelated things. The more you try to ask questions about your human brain, the more you get confused. So it's very difficult to like exactly tell what your human brain did in order to do that when you did that particular action. So since it's capable of doing such wide range of things, it becomes difficult for one model to do all these things. Like for now, we can build one model that can do text to speech or something, and another model to do something else, and then we take a mixture of experts or something like that to combine all such models. But still, it's very difficult for us to make one big model that can do everything. So that's the reason why it is so difficult, and that's the reason of why we have this session now. And now let's start by discussing some early models of human cognition. So in the 400, around 400 BC, like people came up with this idea of associationism, and this idea prevailed till the late 1900s as well. This associationism is a fairly simple idea. I'll start by giving you an example. So say like you observe lightning, and then after that you observe a thunder. You observe that lightning and thunder occur together. You observe that once, twice, and then when you repeatedly observe these two to occur together, your brain forms an association between these two. And it is this association that tells you later on that if you just see lightning and don't hear thunder, your brain tells you that there would have been a thunder after this. Or even if sometimes you just hear thunder and you didn't see lightning, you still see your brain still tells you that there was a lightning before this. So it is the main idea behind this associationism is that humans learn through formation of these associations. And now if you think about this is a fairly powerful idea, because even today all our AI models are like we are trying to associate an input to an output. So it's some sort of an association, but this just saying that information humans learn through associations is very naive, meaning like we get some questions like where are these associations stored, how are they processed, and so on. So this was powerful but not very concrete enough for any practical use. And then came up connectionist models. So by the end of during mid 1800s, people had developed powerful microscopes. People had invented microscopes capable of dissecting the human brain and seeing what exactly is inside it. They could analyze it at the cellular level, and people had already discovered that human brain is made up of large number of interconnected neurons. So this inspired Alexander Bain in 1873 to write this book on mind and body, where he said that information is stored in the connections. And This idea that information is stored in the connection between these neurons, he also came up with some mathematical models for these connectionist models as to how these neurons are connected and how is it that information is stored in the connections. So he even came up with this model. So and let's first discuss some fun fact. Did you know that the number of connections in the largest built AI model today is in the order of few trillions, like some 1 trillion or 1.5 trillion or something like that? Like in ChatGPT 4.0, it is some 175 billion or something, as of what I remember, is the total number of parameters. And if you consider the total number of connections in the largest built AI model, it's in the order of few trillions now. Can someone guess the total number of neurons and connections in your human brain? I mean, just don't Google it because you'll obviously get the answer. Just give some wild guess in the chat. How many neurons or how many connections are there in your human brain? Just give some wild guess in the chat. 100 billion neurons, correct? 100 times more. Yes. So good that you guys have answered. So it's like the closest approximate that we have is the human brain has 86 billion neurons and it has 100 trillion connections, meaning it has 100 times more connections than the largest AI model that has been built till now. So, like this large AI model has it consumes so much power that we require power stations and all, and it is such a power hungry model. And just imagine your brain has been powered by just feeding it 3 times a day. So it's an incredible piece of art made by God. And now let's go come back to connectionist models. So basically, he came up with such models where he had connected these neurons in such fashion. And the most important thing to note here is that the output Z will fire only when A and C fires. X will fire when A and B fires. Y will fire when B and C fires. So here, this network is capable of giving different outputs for different input combinations. Now we say that, so what is there in this? Like we take this almost for granted. There's no big deal in this for now. But back then this was a remarkable thing for them to even conceive that just one circuit or one thing is capable of doing multiple, is capable of giving different outputs for different input combinations. So this idea of connecting these neurons to get different outputs for different inputs was the main thing here. And another important thing to note in his connectionist model was that the output also depends on the strength of the connections. Meaning here, X has been connected to the input A with lesser number of connections, and Y has been connected to input A by more number of connections. So the output Y, the strength of output Y will be more than X because the output Y depends on the strength of these connections as well. So this idea of this is why he said that information is stored in the connections. So if you change this network by altering some of these neurons to some different positions, you end up with an entirely different architecture, and that will give you different set of outputs, even for the same input. So this was the main ideology behind connectionist models. So then came Hebbian learning. In 1949, Donald Hebb he proposed his own model as well, and he even came up with a learning rule. Meaning, like earlier, we just knew that neurons could be connected and in different patterns, and the connection strength could be adjusted to whatever we want. But then, how do we even adjust these connections? How are these connection strengths even determined? So these questions were kind of unanswered, and he came up with a learning rule to find those connection strengths as well. uh, so the main idea behind his learning rule is that neurons that fire together wire together. This is a very nice summary of his learning rule, because what it says is if two neurons which are connected to each other, if they are activated simultaneously again and again, then the strength between of the connection between them becomes stronger and stronger. So this is a pretty remarkable thing which shows how your human brain, the connection in in your brain evolves. So like if two neurons are continuously firing together when you see some input, then the strength bit of the connection between them becomes stronger and stronger. And he even proposed a learning rule, Hebbian learning, but unfortunately later on it was proved to be unstable. Meaning, it was proved that this, if you follow this learning rule, you may not always converge. The learning rule might not converge for every starting values of these connection weights. So and this is the reason why we won't go into much details of this learning rule and the model that he proposed. But the main idea behind his model and learning rule is that how are these networks trained? How are these connection weights updated? If neurons fire together, then they wire together basically. So coming back to the roadmap, so we discussed about some early models of human cognition, and we saw how kind of associationist ideas came up, then how connectionist models were developed, and we even discussed Hebbian learning quite a bit. And now we'll move on to our most favorite, that is perceptron. This is the most important thing, and yeah, let's start. In 1958, Frank Rosenwald came up with a model for the neuron. So basically, this is an image of the human neuron, human biological neuron. Here, all these branches that you can see, like uh, these branches and these branches that you can see, these are connected to several other neurons. Like this branch is connected to another neuron. Here also, several other neurons are connected to this particular neuron. So this is how this particular neuron is connected to many other neurons. And so he came up with a mathematical model for this neuron. Like he just said how this neuron can be modeled, and then came up with the idea of connecting these neurons to form what are known as multi-layer perceptrons. So we'll go over that later on. So what he said was, this neuron is connected to some several input neurons and it gives some output neurons. So today we understand that like all these neurons communicate by electrical impulses. So some set of neurons fire, which are giving input to this. If some of them fire or just give some electrical impulse, if it is greater than some threshold, then this particular neuron will fire, something like that. So he also gave us a fairly similar model where he said that, say you have some inputs x1 to xn. For now, let's assume that these are just real numbers, and these are associated with some weights, meaning this neuron, this perceptron, he called this as perceptrons model. He called as perceptron, and the biological one is known as neuron. Later on, you'll see that we'll use perceptron and neuron interchangeably because they're kind of the same. So then he said that the neuron would have learnt certain weights for each of these input neurons. So an analogy could be like during your JE time or whatever before your exam, you would have access to several information sources. Like your teachers will be giving you some information, your friends will be giving you some information, and you watch YouTube videos or something. So you have access to information from many input sources. So now it is your responsibility, or like it is you who decide whose information do you give more importance to. For example, you may give more importance to what your teacher says than what your friend says, or sometimes it can even be vice versa. But like, so it's like you have in your brain, you have stored these connect your weights. By weights are basically how much importance do you give for each of these inputs. So, and then what we basically do is we take the weighted sum of each of these inputs. So like w1x1 plus w2x2 plus w3x3 and so on. And if this weighted sum exceeds the threshold t, then the output, this perceptron will fire, meaning the output will be 1 only when sigma wixi is greater than equal to t, or it will be 0 when sigma wixi is less than t. So this was a model that he came up with, which was a fairly simple model, but it still is a very powerful model, as we'll see later on. So I hope this is clear. If you guys have any doubts regarding what this perceptron model is, you can unmute and ask, or you can even put it in the chat. One more thing to notice, like if we bring this threshold to the other side, like sigma wixi minus this threshold, then this negative of threshold is also called as bias, meaning sometimes we just write sigma wixi plus b greater than or equal to 0 plus b less than 0, something like that. So it's just for convenience sake. So now I assume that you guys don't have any doubts and I'll proceed further. Now he even came up with a learning rule for this particular perceptron, meaning like how are these weights learned? Even threshold is also something that we have to learn. Like it's like your tolerance, like till when will you tolerate the inputs? Like after that, the perceptron fire, something like that. So now the learning rule that he gave was, say your for some input x, your model outputted y of x, meaning the predicted output is y of x, and the desired output, meaning the true output that you wanted, was d of x. So then what we do is we take the difference between the desired and the predicted, that is the error term, and then multiply it with the input and some scalar, scale it by some factor alpha, and then update your weight. So you initially start off with some random weight configuration, meaning all the weights are initially randomized, and then each of this weight is updated by this quantity, that is alpha times the error times the input. So then, eventually, if you do this again and again, meaning you update all the weights simultaneously by this quantity, then again take the output of that new model which you get and do this iteratively again and again. Then he proved that, he even proved that, like he just didn't say, he in Hebbian learning it was mostly like what he said, but here he even proved that this learning rule will converge for linearly separable classes. Meaning, if the input classes are can be separated by just a linear boundary, then he said that this learning rule will give you that perceptron model that can separate these two classes. So this was a very remarkable thing, and also due to the fact that he proved that this will converge. So now we'll go over Boolean gates or basic thinking machines. This is slightly off topic. Like this does not fall in the timeline that we were following. Like we were going in the order of how things evolved. But I just still wanted to cover this one topic because this is very helpful in explaining how powerful these multi-layer perceptrons are. Like we'll see that an MLP can model any Boolean function. So for that sake, we need to have a basic understanding of what Boolean gates are. If you already know this, it will just be a recap, so no worries. So in 1847, George Boole came up with this mathematical construction of a logic gate. uh, Back then this was just a mathematical construction, meaning like it was just in people's mind. At that time this did not have any applications, so this was only in the math world. But then in 1947 people invented, when they invented transistors, they saw that this logic gate which he had modeled can be implemented using a transistor. So this was when the we saw the intersection between maths and science, meaning like we could implement whatever we thought in hardware and make a transistor do to implement this such logic gates. So one more interesting thing to note is that the transistors were invented 1 century after he gave this model of logic gates, exactly 1 century. So it's like it also shows the power of abstract math. Like even initially it seems to have no useful applications, but then later on people might discover some useful applications of that as well. So now let's get back to what these Boolean gates, what did he even model? So he said that say if we restrict all inputs and outputs to just zeros or ones, so either they'll fire or not fire. So this restriction can help us in modeling the information transfer or something like that. So say like if the input is now here, first thing that we'll discuss is a NOT gate. This is also known as an inverter, where the output of this will be 1 when the input is 0 and 0 when the input is 1. So it's like whatever the input state is, it will just toggle it and give it as output. Then this is OR gate, meaning this will, the output of this will be 1 if any one of the input is 1, else it will be 0 only when all of them are 0. This is AND gate, where this performs the logical AND of both the inputs. All these can have multiple inputs as well. Like I mean, NOT can have only one input, but the other gates can have multiple inputs as well. In case of AND gate, the output will be 1 only if all the inputs are 1, meaning you want the first input to be 1 and the next input to be 1 and the next input to be 1 for the output to be 1. So these are the basic, most fundamental gates that he modeled. And then this is known as an exclusive OR gate or XOR gate. Here the output will be 1 if there are odd number of ones in the input string. So as you can see, like for input 0, 1, the output is 1. For 1, 0 also it's 1, and so on like this. This is a NOR gate. This is just the complement of OR gate, meaning you first take the OR of all the inputs and then pass it through an inverter. The output of that is this. This is a similar complement of AND gate, also known as NAND gate, which is just the complement of AND gate. So I went a bit fast in these two slides because like I assume that you guys have a bit of an understanding about how these logic gates work and things like that. So now let's go on to what all can one single perceptron learn. So now comes the answer as to why did we even discuss this Boolean gates or logic gates in this session. So we were trying to understand the human brain. Then we came up with perceptrons that can model the neurons. And the reason why we discussed this is because we'll see that a perceptron is capable of modeling all these logic gates. So this is the first perceptron model for a NOT gate. So basically you can just verify for yourself itself, like if minus 1 times x is greater than equal to 0, then the output is 1. So meaning if the input is, if you just verify, you can just verify yourself, like if the input is 1, the output turns out to be 0. If the input is 0, the output turns out to be 1. Here that greater than equal to, that equality signs is also important here. So this is a perceptron model for a NOT gate, and this is the perceptron model for OR gate, meaning like here we take, like say you can just verify yourself itself, like 1 times x1 plus 1 times x2, if it is greater than equal to 1, then the output is 1. So for that, even if any one of them is 1, then 1 plus something will something positive will always be greater than equal to 1. So that's why the output will be 1 if any one of them is 1. And this is the perceptron model for AND gate. Here, like you want both the inputs to be 1, only then it will be greater than equal to 2. So this can model AND gate. So like we saw that these perceptrons are capable of modeling these basic logic gates, and here all the inputs are Boolean inputs. And one more thing is, like, we can even model NOR and NAND gates in similar fashion. Like we just have to change some of these signs, and we get similar models for NOR and NAND gate as well. But now comes the question: can we model XOR gate? Okay, so what is the XOR gate? If you guys don't remember it, this is XOR gate. The output will be 1 if there are odd number of ones in the input. So for now, just take a minute and try out. If you have just two inputs, A and B, both are Boolean, and the output is also Boolean, you want to model XOR gate using a perceptron. Meaning, tell me the set of weights, what should be the first ones, both these weights, and the threshold for which that model can represent XOR gate. So you can take a minute and try this. Uh, Put the weights and threshold in the chat. You can even unmute and answer, because this is not a straightforward question which has a straightforward answer. Okay. Uh, Nice that you guys didn't answer, because this question doesn't have an answer. And the answer is you cannot model XOR gate using a single perceptron. So I'm happy that no one answered. And the reason for that is very simple. If you consider this input space, x1 and x2 are the inputs. Here, like each of these four circles, which you can see, are all the possible input combinations, meaning 0, 0, 0, 1, 1, 0, 1, 1, and all. This represents all possible inputs, and the number inside that circle, that is 0 or 1, represents the class, that is the output. So as you can see here, for AND gate, all the zeros and the ones can be separated by using just a single straight line, meaning this one straight line divides, can separate both 0 class from the 1 class. Similarly, in case of OR gate as well, this one straight line is capable of separating the zeros from the ones. So basically, we require just one straight line for modeling AND and OR gate. This was the same case even with inverter as well, because like there you had just one input and you had to classify, separate zeros from ones. So you just draw a line in between and that can separate, something like that. So, but in case of XOR gate, if you draw a similar diagram, you'll see that when the one class and the zero class cannot be separated by using just one straight line, meaning this gate is designed in such a way that you require at least two straight lines to separate the ones from zeros. Like just think, like can you just draw one straight line that can separate both zeros from ones? That's not possible. So we require at least two straight lines for separating these two. Now, that was the reason why we cannot model XOR gate using just one single perceptron. We require at least two perceptrons to model XOR gate. And this gives rise to the idea of multi-layer perceptrons. Now, an interesting thing to try out is you can also ponder over like what happens if we have three inputs. Meaning, say you have one input is x1, x2, and x3. You can take a minute to answer this. Like just think about what will happen if we have three inputs and we want to model this three input XOR gate. Okay, I'll ask this question after discussing how XOR gate is even modeled. That would be better. So now we discussed about perceptrons and now we'll be going over MLPs and also discuss how powerful they are. So this is the XOR gate implementation of implementation using a perceptron multi-layer perceptron model. So basically, what we do is the topmost this particular perceptron neuron is expected to learn one of the straight lines, and the bottom perceptron is expected to learn the other straight line. So basically, we saw that one perceptron can learn one linear boundary. So you take two perceptrons, make one learn the first one, the other learn the second one, and in such a way that the first one will output one when the input is on this half of the plane, and this will output one when we are on this half of the plane, meaning both of them will output one only when you're in between them, something like that. So now what we want is basically the logical and of both of these, meaning we want our final output to be one only when both of this tell that I'm on the same side of each other. So that is why this last perceptron over here, this model, if you remember, was is same as AND gate that we discussed. So we pass the output of both these perceptrons to through this AND gate and check if the input is between both these straight lines. And when the input is between both these, that the output is one. So this is basically XOR gate. So we can implement XOR gate using a multi-layer perceptron. We require this such two layers and two perceptrons. It is not possible for just one single perceptron to model this. So the moral of the story is that one single perceptron, it's a weak computational unit. It cannot do very complex tasks, but we can achieve complex computational systems by networking these and connecting these in appropriate fashion. So now you can take a minute to answer the question that I asked earlier, meaning like what if you have three inputs, x1, x2, and x3, and you want to model three input XOR gate using this particular using a multi-layer perceptron of this kind. So the question is, how many perceptrons do you need in the first hidden layer? Meaning in this layer, you have three inputs here. How many perceptrons do you think you require in this first hidden layer to model this three input XOR gate? For this, you just have to visualize into how many different regions are there and how many linear boundaries I need in order to separate them. So if you just visualize, by the way, when we want to extend it to three inputs, the definition of XOR gate is the output will be one if there are odd number of ones. So, okay, I'll wait. Minus one, minus one, minus one for NOR. Okay, so you meant like NOR gate can be modeled using these particular weights and threshold. I think yes, because for OR and NOR, only difference is that you have an inverted output, right? So it is basically whenever the model outputs one, you want it to be actually zero. So you just multiply the whole equation with minus one, meaning that sigma WXI greater than equal to T. When you multiply with minus one, then the inequality will reverse. So that is basically what you wanted. So this works. Good, Rishit. I hope the question is clear. The question is when you have three input and you want to model the three input XOR gate, how many perceptrons minimum, like just don't complicate this network. At minimum, how many perceptrons do you need in the first hidden layer in order to model this? Or at least the basic one. Like you can implement like three input, like XOR can be implemented like first you take XOR of x1, x2, then you take the output of that and XOR it with x3 as well. That is also possible implementation. Uh, Okay, I think that is what Rishit is telling. Like he said, you first take the XOR of. Okay, I think what you guys thought is you take first any two inputs x1, x2, take the XOR of them using similar fashion. The output of that, then you take XOR of that with x3. Yeah, you construct similar model. The output of that is the XOR of all these three. This is also one possible implementation. Another one that you can think of is in this three-dimensional plane that you have, your input 0 comma 0 is the output corresponding that is 1. Sorry, output corresponding to that is 0. Then you have three of these edges. Like if you move along, you can imagine it like a cube in three dimension. Whenever you move along one edge, you toggle one of the 0 to 1. So you change the parity of that. I mean, basically, like the initially from origin, when you start moving along one edge, you get you move from 0 to 1. So these three, there'll be three such points which will have the output to be 1. Then you will have again three such vertices for which you have the output to be 0. Then the last one, 1 comma 1 comma 1, will again have output of 1. So it's like you have four different uh, classes. No, I mean not four different classes. If you try to imagine, there are four different planes, and these four things can be separated by just three planes. Like you just draw one plane between this origin and these three to separate them, then another plane, and then one last for the last one. So that is also a way of implementing it with just three perceptrons in the hidden layer. You can in this case you seem to get a lower number of perceptrons because you are increasing the depth of the network, meaning you're going deeper and deeper. This is a very important thing which we'll discuss later on as well. That is, if we make a very deep network instead of a longer network, if you make a deeper network, that is much better. So it'll may reduce the number of neurons that we require as well. So that we'll discuss later on. Nice that you guys answered now. So now comes the most important reason why we discussed Boolean algebra here. This here is what is known as a truth table. I think you guys must be familiar. Else, like it is a simple thing. You have some Boolean inputs, and the output is also Boolean. And in our truth table, we enlist all possible input combinations. Meaning here we take all possible input combinations and write down the corresponding outputs. So this function that takes these as input, x1, x2, x3 as input and produces y as output is called as a Boolean function. And George Boolean proved using his theorems of Boolean algebra that you can model any such kind of function, meaning you change this to anything. You can model that using just and, or, and not gates, meaning these basic gates are sufficient to model any Boolean function. You can network them to form any complex combinational circuit to model these any Boolean function. So basically, this is a 3 to 8 decoder. You can just look up this later on if you want. Here, all this the it is basically like if the input is 0 0 0, this particular AND gate will output 1, and all the others will be 0. If the input is this, then this particular AND gate will be 1 and the rest all will be 0. So by this reasoning, we want the output to be 1 for this particular input combination and for these two, right? So we just take the output of these AND gates and then pass them through an OR gate. So the output will be 1 when either this is the input combination or this or this. So we don't even need this other extra AND gates. They're just for uh, just to show you that we can extend the same logic for other functions as well. So if you have a 1 here, you can even take this and pass it through OR gate. So that was the idea. So you here the only gates that we're using is not and OR gates. So we can, this is also known as sum of products. You can even look up that later on if you want. But the basic idea is you can model any Boolean function using just a combination of these basic logic gates. Now we saw that we can model them using perceptrons as well. So yeah, a single perceptron can try to model all these gates. So what we can do is we can replace these gates by using these perceptron models, and we can construct a connected network of all these perceptrons to learn such Boolean functions. So this proves that our multi-layer perceptron is capable of learning any Boolean function. You can try make it learn any Boolean function. So that was the, this shows how powerful they are, and this was the reason why we discussed about Boolean algebra in this session. Do you guys have any doubts till now? You can unmute and speak or just put in the chat. Okay, no, fine, thanks. Now I'll proceed now. So now, till now, what we did was we discussed the case where our input space was confined to just Boolean inputs, meaning it's either 0 or 1. And even our output space was confined to either 0 or 1. So now let's try to extend this notion to all real numbers, meaning what if my input can take any real number except not just zeros or ones? So what will the perceptron learn in such a case? So now it is just the same logical extension. You just have to extend the same argument here as well. Here, the perceptron model is also the same. You have these n inputs, you have these weights and this threshold. The output is 1 or 0. Only changes here, the inputs can be any real number. The weights are also any real number. Threshold, any real number. For now, let's keep the output to be either 0 or 1 itself. Either it fires or not fires. So let's start with extending the input space to all real numbers. Later on, we'll even see how we can extend this output space also to all real numbers. That will come later on. So for now, let's see what happens when we extend this input space to all real numbers. So what can this single perceptron learn? So it basically learns the separation between a linear boundary, two classes which are separated by a linear boundary, and that equation of that boundary is given by this sigma wi xi is equal to t. So this is a linear equation in all these inputs, right? So you have w1 x1 plus w2 x2. All these inputs are raised to the power of 1. So it's a linear equation. And that is the reason why we have a linear boundary separating both these classes, the zeros from the ones. So this boundary is what our perceptron is trying to learn. So let's try to visualize this, how this looks. So say if you have three inputs, it's easiest to visualize in 3 dimension. You can even do it in 2 dimension, but this is much better, I feel. So here you have three inputs, I1, I2, and I3. In this three-dimensional space, you want to learn the boundary that separates all these red dots from the blue dots. So this green plane that you can see here is the boundary that separates these two. Here, you can learn this boundary using one single perceptron, because we can adjust these weights and threshold to match the equation of this. And so we can expect this to learn this particular boundary. Uh, and this is the bias thing which I said earlier. So I hope this is clear. The fact that a single perceptron is capable of learning a linear boundary, and it could be any linear boundary, because we can adjust these weights and threshold to any value that we want, because we have extended it to all real numbers. So now, okay, so I can learn linear boundaries, meaning in 2 dimension. If I'm in 2 dimension, I can learn a line that can separate two things, two regions. So now, what if that line is a very simple thing? I want to extend this to much larger or complicated boundaries. So say we have the task of classifying this quadrilateral, meaning if the input is somewhere inside this quadrilateral, the output is 1. If the input is outside this quadrilateral, somewhere here, the output should be 0. So it should be 0 everywhere in this white region, and it should be 1 inside this blue region. So can you come up with a MLP model which can do this? Basically, you can assume that there is some x1 and x2 two input axis like this, and each point is associated with some coordinate. Now, if that point lies inside this, you have two inputs x1, x2. The output should be 1 if that point ka coordinate is inside this quadrilateral. Here I'm not exactly specified where the coordinates are or what are the coordinates of A, B, C, D. So you can just tell me how many perceptrons do we need in the first hidden layer. So in the first hidden layer, how many perceptrons do we need as in a simple model to learn this quadrilateral boundary? You can put your answers in the chat, or you can even unmute and speak. Like, the question is, how many perceptrons do you need in the first hidden layer in order to model this? 8. Okay. Um, I didn't ask the total number of perceptrons. I mean, 8 is also not. 8 is too much. Like, can you reduce it? 4. Okay. Uh, Anyone else? Like, I can give you guys a hint. So this figure over here is a hint, and you can take inspiration from the previous slides what we have discussed till now. How we can extend this idea shown in the second figure in order to model this quadrilateral. how do you figure out that, oh, four linear boundaries? Okay, fine. I think the answers come out in the chat. So the true answer is you just need four perceptrons in the first hidden layer to model this, because in this figure you can see that I have shown this orange line of separation, right? So you can have one perceptron to learn this straight line BC. So the output of that perceptron will be one if you're on this orange region, anywhere in this region, and it will be zero anywhere if you are in this region. So then what we can do is we can extend the same argument with another perceptron and say that that has learned the side AB, and another one which has learned side AD, and another one which has learned side DC. So meaning this AB perceptron will output 1 when you are on this side, on the right side of AB. AD will output 1 when you're on the when you're below AD, and DC will output 1 when you're on the left side of the line DC. So then how do we figure out if you're inside this quadrilateral or not? So it is basically only when all of them tell that I am inside this quadrilateral, meaning when BC says I'm above, AB says I'm inside on the right side, and AD says I'm below this, and DC says that I'm on the left side, then we can say that I'm inside this quadrilateral. And this is true for every point inside the quadrilateral. So then what we can do is we can pass the output of all these four perceptrons through an AND gate to get the final output. So this is how this looks like. Here you have those two inputs, x1, x2. Each of these four perceptrons here, you can think of them as learning one of the lines of this quadrilateral, and this is the final output perceptron, which is basically an AND gate. So this thing that you can see here is a 4-input AND gate, because what it does is 1 times this plus 1 times this plus 1 times this plus 1 times this will be greater than equal to this output is either 0 or 1, right? So it's the same case if you consider this as a single model. Like here the inputs are also Boolean for this perceptron, output is also Boolean one. So it is basically some sum of four either zero Boolean numbers is greater than equal to 4 only when all of them are 1. So it means that when this perceptron tells that I am on one side of the side, and similarly all these will agree, only then the output will be 1. And when they agree, that is when you are inside the quadrilateral. So the equivalence between being inside the quadrilateral to all sides telling that I'm on inside is what you have to see here. So I hope this example is clear, because this is the same thing that we'll extend further on to build more complicated things. So if you guys have any doubts, you can ask now, because we'll be extending the same thing. So okay, so I assume that this is clear enough. So now let's try to extend this decision boundary, meaning like first we started off with just one linear boundary. That is, we started off with one line. Now we say that we can learn any polygon. Basically, we can extend this to a polygon as well. If we have some n sides, you take n perceptrons. Each of them will learn one of the side. And when all of them agree, you have an AND gate in the output perceptron. And that is when you are inside this polygon. So we can extend this idea to any particular polygon. That is what we saw now. But now, what if we want to extend this decision boundary to something more than a polygon? So say here we have the union of two polygons. What do we do if we have something like this? It is similar itself. Here first what we do is we take 5 perceptrons to learn the bottom pentagon. So each of these 5 perceptrons are expected to learn one of the sides, and then as usual we take the AND of all of them. So this output will be 1 if I'm inside this particular pentagon, else it is 0, meaning even here it is 0, here also it is 0, here also 0, everywhere 0, only inside this it is 1. Now what we can do is we can extend the same argument with another set of 5 perceptrons and tell them to learn these 5 edges, and when all of them say that I'm inside this, we take the AND of them. This is the output of this particular perceptron will be 1 when I'm inside this pentagon, and this will be 1 when I'm inside this pentagon. Now our goal is to the output 1 when I'm in either this or this. So this is what an OR gate is meant for. And as we saw earlier that we can model OR gates, AND gates, all using just such perceptrons. So we just take the OR of this, we add another perceptron in the next layer, to take the OR of both this, and this will learn this particular decision boundary. So this is how we can extend polygons to union of polygons or intersection of polygons by union using or, intersection using and. So we can extend this idea to several different complex decision boundaries. So now this is a very useful thing because it shows how powerful just such MLPs are. Now, the next thing is, can we extend this to arbitrarily complex decision boundaries? Meaning, can you model this dog? The output of this should be one only when you're inside this dog, and when you're outside, the output should be zero. So it is very straightforward from the previous example that this is very simple. We just divide this dog region into several polygons, and then we take the OR of, we'll take some perceptrons for learning each of those polygon, then take the AND of those, and then in the final layer, you just take the OR of all those. So it's basically you're dividing this into several polygons, learning each of them individually, and then taking the OR. And the idea is, if you take larger number of polygons and larger number of perceptrons, you can model this to arbitrary precisions. So theoretically, you can model this to arbitrary precision because you can take any number of perceptrons you want. Uh, but practically, it is difficult to implement, which we'll resolve later on. But ideally, at least theoretically, we can model this using to arbitrary precision. So this gives rise to an idea that we can model any complex decision boundary using multi-layer perceptrons. So now what if we extend this to higher dimensions? So till now we discussed in 2 dimension, meaning we had one straight line which could learn the two half planes, and then we took the AND of all those such straight lines to learn some polygons, and then we took the union of all those to learn some complex decision boundary. So now what will happen if we extend this to higher dimensions, meaning instead of 2 inputs, we have 3 inputs or 4 or many. So what will happen? Does this same argument still hold? And the answer is yes. We can still extend this to higher dimensions to learn any arbitrary complex decision boundary. So intuitively, it's like if you have, say, 3 dimensions, in 3 dimensional space, a perceptron can learn a plane. Like in the, I think, few slides before, I showed that we can learn a plane that separates 2 regions. Then we can take 2 such planes or 3 such planes or many number of such planes to learn boundaries. So it's like we have some polyhedron and we are learning its faces. So each of this perceptron can learn one face of that polyhedron, and we can learn the regions inside and outside of that polyhedron. And then we can take union of many such things to learn any complex decision boundary. So this is how theoretically we can extend the same argument that MLPs can learn any complex decision boundary. And the same thing is valid even for higher dimension. If we go to some 5 dimension or 784 dimension as well, it's still valid. Now, why did I take 784? Because that will come later on. So the main idea behind all this discussion till now is that MLPs are universal classifiers, meaning I think this is clear now. If you guys have any doubts, like what does it mean to say it is universal classifier, is that it can classify or learn any region in any dimensional space. You just have to have a sufficiently large enough network to learn that. If you have that, then fine. So do you guys have any doubts now, or shall I proceed? Okay, fine. So I'll proceed now. So what can we do with this? Like, so what if we can classify regions? Like, what is the use? Why did we even discuss this? So say, consider this is one practical application of this. Say you want to classify handwritten digits, meaning you this data set is known as MNIST dataset. It has a collection of large number of such handwritten digit images. Each of this image is a 28 cross 28 image which has 784 pixels. So you can imagine it as some 784 dimensional vector where each of this you have 784 inputs, and your output should be either it is a 0 or a 1 or a 2 or so on up to either it's a 9. So in the 784 dimensional space, you want to identify which region corresponds to 2, which region corresponds to 6. If you're able to do that, then you can identify which digit is it is. So if you can identify the region where all twos are, then that solves the task. And we saw that MLPs can identify any region or any classification boundary. So we can use an MLP of sufficiently large size to learn this particular task, meaning we can have a large enough MLP that can recognize handwritten digits. So this shows how powerful MLPs are, and how uh, we saw MLPs becoming more and more powerful as we saw different applications. The more we delve into this, we feel it is more powerful than we expected it to be. So this was a nice application of this. I hope the purpose of classification is clear now. So now, till now we have seen all this, like we started with these connectionist models, perceptrons. We then connected these perceptrons to MLPs, and then we saw all this power of MLP and all. So now we'll be going over to neural networks. What are they, and why do we use them? So just on a side note, this in this session I'll be using neural network and MLP almost like interchangeably, because there isn't much of a difference between them. But to be uh, to be accurate, a neural network is a larger or much broader term, which can be referred to recurrent neural network (RNN) or convolutional neural network (CNN) as well. So it's a much larger term. But for now, for the sake of this session, for convenience, I'll be referring both these interchangeably. So this is the structure that should come to your mind whenever I say either of this. So just imagine such a feed-forward, fully connected network whenever I say either a neural network or an MLP. So this was kind of a disclaimer, but fine. So now moving on. So till now, what we saw is how do we learn classification boundaries. So here, if you observe one thing, we had the output space to be confined to discrete classes, meaning the output is either 0 or 1 or something like that. So the output space was confined to discrete classes. But now, what if we want to extend this idea to outputting any continuous real number? Meaning, in this particular slide, I said that we will extend this Boolean inputs to any real numbered input. Now we are saying, okay, now inputs are real numbers, but till now the output was also either Boolean or some discrete classes. Now, what if we want to extend the output space also to any real number? So this task is known as regression, where we want the output to be a continuous real number instead of just discrete classes. So this is what we'll discuss from now on. The task is named as regression, where we want to learn a function that outputs a real number. So the question is, can we use MLPs to model such functions? So till now, our output space was confined to just discrete classes. Can we extend somehow the same MLP architecture for this as well? And the answer is yes, we can do that. So say we have some two inputs, say we have one input x and one output f of x. Now, how we can do this is, one approach would be, now you take two perceptrons, let the weights be 1 and 1. Then say the threshold is some t1 and here threshold is some other t2. So what this perceptron learns is this step function. This is also known as a step function because it looks like a step. I mean, so here this also learns another step but with a different threshold. Then what you do is you add another perceptron here which takes the difference between these two. So when you take the difference between these two, you get this pulse kind of a function where the output is 1 when you are between t1 and t2 and 0 everywhere else. So now, what can we do with this pulse function? Can we approximate any function? Yes. So we'll see how. So say you have this purple colored complex function which you want to approximate. Here the output is a continuous number, as you can see. Now what you can do is you can divide this into a large number of bins, and in each bin you learn one particular pulse function. So you can this pulse function will output 1. So you just have to scale each of this. You assume that these two perceptrons have learned one pulse function. So this red circle that you can see here is to scale both of this by this factor h1, which is this height, so that this will output h1 and this will also output h1. When I subtract, in between the output is h1. So basically this pulse function has been elevated using 2h1. So similarly, these two perceptrons, I can elevate them by a factor of h2, and so on. I adjust the heights of all such pulse functions, and then I get this kind of an approximation, this kind of thing. So now the idea is, as you increase the number of such pulse functions, like if you decrease the gap between these two thresholds, you get smaller bins, and as you take larger number of bins with smaller width, then your approximation becomes closer and closer. So this approximation that we currently have becomes much better when we take more number of perceptrons with lesser threshold gap, and accordingly scale them through proper heights. So we can have a large MLP that can approximate any continuous function. And the good thing is that, okay, fine. So now let's first see this in action. So here, what I'm trying to do is, I have this single one hidden layer MLP where I have some hidden neurons, hidden perceptrons H1 to Hn. And what I'm trying to do is, I'm trying to increase the number of perceptrons in this layer. And for each time, I'm training this for some, I think, 1000 epochs or something. And after the after training, I show how this has performed. So I've also linked the Google Colab code over here. You can check that out later. So I'll play this again. So here, this MLP is trying to approximate sine function. So here I'm changing the number of neurons, as you can see here. With 22 new perceptrons, this was the approximation. With 40, it is this. So this shows, if I increase the number of perceptrons in this hidden layer, the approximation becomes better and better. Now here there's one small catch that I didn't tell you till now. That is, here I have not used threshold as activation function. I've used a relu activation function, but we'll get to that later on. There are some issues with this threshold activation function, because of which I used relu activation function. I'll discuss this later on. But the fact that I wanted you guys to note here is that, as I increase the number of perceptrons in the hidden layers, the approximation becomes better and better. You can approximate it to with higher precision. So that was the key takeaway from this slide. Here you can also see how this same network is trying to approximate some other random arbitrary function. As n increases, the approximation becomes better and better. So with 99 such perceptrons, this is the kind of approximation that you can get. And you can see that this is quite accurate enough. We can make it much more accurate by increasing this to higher values. But for now, this was the key takeaway from here. So now comes the most important part of this session, that is Universal Approximation Theorem. So formally it states that any feed-forward neural network, forget this feed-forward term, any fully connected meaning each neuron in every layer is connected to every other neuron in the previous layer. So that is what I meant by fully connected network, with just a single hidden layer. So for now, let's assume that there's only one hidden layer. So this theorem states that even if you have just one hidden layer and some finite number of neurons, you can approximate any continuous function to arbitrary precision on a compact subset of real numbers given an arbitrary activation function, appropriate activation function. So the main idea is that a single hidden layer is more than sufficient to learn this. But this is theoretically possible, is what this theorem proved. This was the heart of why neural networks could do so well. And just imagine, before ChatGPT came, when they had to train, or whatever, before the first neural network came, when they had to train, ChatGPT was initially was trained on, it was such a large network with so many thousand millions of parameters in it. So what was their motivation for it, that it will learn? Like, how did they believe that training such a network will even learn such a function that we want? How did they believe that such a network can learn something like some handwritten digit classification thing? How did they even believe that? That belief came from this theorem, that a neural network can model any continuous function. So that is why this theorem is so powerful and important. So now, till now we have seen that MLP is a universal Boolean function. MLP is a universal classifier. You can learn any classification region. MLP is a universal function approximators, meaning you can approximate any continuous function. So MLPs are are very powerful, is what we have seen till now. So let's just take a break for some 5 minutes now and come back again. We'll again discuss some more ways by which we can improve upon MLP. How can we make it better? Like here, one of our key assumption was that we have access to arbitrary number of perceptrons or neurons in that hidden layer. That is why we said one hidden layer is sufficient. But in real life, when we want to implement it practically, we won't have so many neurons or perceptrons. We'll have some finite number of perceptrons. So how do we achieve the same task with lesser number of perceptrons, and how to make it more powerful and expressive? So we'll discuss all this after the break. So you guys can take a 5 minute break and come back. If you guys have any doubts, you can put that in the chat as well. Um, you guys can hear me, right? Just can you put a thumbs up or something? I didn't see. Can you guys hear me? Okay, fine. So let's continue now from where we left off. So as I said that now we'll discuss some techniques by which we can make this MLPs much more powerful and efficient. So one second. Uh, one second. Um, yes. So can we make it better? So how do we make this better? So in this slide I had told you that in this slide I had shown you how increasing the number of perceptrons in the first hidden layer will increase the precision of how to what extent we can approximate this function. So now we'll see how it affects if we increase the depth of the network. Meaning instead of stacking these perceptrons one below the other, how is it better if we stack them one after the other in different layers? So that is what we'll see first. That is how does depth matter, and we'll see that that depth affects a lot, and it is much more better to make the networks deep instead of networks being wide. Then we'll go over activation functions, meaning like in the few slides before we saw that we can approximate any continuous function, but there what we did was our perceptron inherently was using that threshold activation function which is discrete. So we are trying to approximate something continuous using a large number of such discrete ones. So it would be better if we make the building block itself as perceptrons were our building blocks, right? So it would be better if we make those building blocks itself as continuous instead of being discrete. So that is where the idea of activation functions comes into picture. So we'll discuss that as well. These are the two main things that we see to make this networks better. So now comes the most awaited part of this session, this origami thing which I said in the start. So here I'll be showing you guys a demonstration of folding a paper. So just watch that carefully, and I'll try to link this to what we're trying to discuss now. So yeah, so this is our first demonstration. So what we do is first we take a square sheet of paper, then fold this into a half. After the first fold, we have two regions in that paper. Then we again fold it along the other diagonal, and after that we achieve four different regions. And we continue this process again and again. We fold it for the third time, after which we have six regions, and then we again fold it for the fourth time, after which we'll have eight regions, and so on. So you can just visualize this process, and this is a very simple thing, and the reason why I kept this is because this is very intuitive. This gives you an intuitive answer for what we are trying to discuss now. So just try to think how this is related to what we are discussing. So after the seventh fold we have 14 regions, and after the eighth fold we have 16 regions. So you can see those 16 regions, right? Like you have four boxes, and each of those boxes you have a cross with four such triangles. So now my question to you all is, here I took 8 folds to make the 16 regions. So the question is, can you come up with a way by which you fold the paper less number of times but still achieve the exact same 16 regions? Meaning you should have these 16 regions in the same format, like this diagonal sides and all, but you have to do achieve the same thing with lesser number of folds. So how would you do that? So you can think about it for a minute and let me know. It is better for this particular question if you unmute and speak, because this is difficult to type out, but still if you find typing is better, so I hope the question is clear. How do you achieve the same 16 regions in less number of folds?
Like we could fold the paper once again before unfolding it to like get the symmetry. Like
Oh,
we
you're.
fold it off the diagonal.
Hmm.
We like if we fold it across the diagonal and then again fold it once the corner towards the center, we'll get the ones parallel to the diagonal as well.
Okay.
Once
Nice. At least you guys are trying to think. And I think you got the main essence of this as well. Fine. So now I'll reveal the answer. He was very close to the. I think he said the correct answer as well. Just check if this is what you told. So I'll be showing you the actual demonstration of how it works. So basically, after your first fold, you just don't open it. You continue folding from where you left off. So after the first fold, you would have two regions as usual, and then you don't open it. You continue with the second fold again. So after the second fold, you would have four regions. Then again, you do the third fold, and after this third fold, I'll show you that you have eight regions instead of just six. You don't need to open this. I just wanted to show you guys that there are eight regions after three folds. That was the reason why I opened. So now, if you had continued with this fourth fold, as you can see now, after this four folds, you will have exactly 16 regions as before. So now, uh, okay, so can someone guess why and how is this related to what we are discussing? Why did I go over this paper folding thing? I think he got the essence of, Rishad got the essence of what this means. So the basic idea is, one second. Huh. So now, in say this is some axis x1 and x2 in this two-dimensional space. Say that this is your paper. Now what you did was, when we folded this once, we learn one particular straight line which can classify the paper into two regions. So if you see it from this perspective, each fold is considered as one perceptron, because every fold will give you a line which can be learned using one perceptron. So basically what we did was, first in the first demonstration, we had inputs as x1 and x2, which was this original paper. Then we passed that to one particular perceptron to learn the first uh, straight line, first fold. Then what we did was, we again we unfolded this back, and again did our second fold with the same paper. Meaning, we didn't we gave the same inputs to another perceptron. This is what we achieve after our second fold, and so on. We did the same thing with more number of perceptrons. So we took eight such perceptrons. For each of these eight perceptrons, we gave the same two inputs. That is, we gave the same paper as input. So, and then the region that we get after combining all these eight perceptrons was our output. That is, these 16 classes. This is not an exact concrete example, but there is an analogy which gives you an intuitive feel. So now, what we did in the second case. Now let's see what we did in the second case. So we had the same x1 and x2, and we had our paper. So what we did was, after the first fold, we had x1. We took the paper x1, x2, pass it through a perceptron to make the first fold. Then what we did was, instead of opening it and giving the same paper as input to the next one, we passed the output of this perceptron to the next one to form this particular fold. Then we pass the output of this perceptron to the next perceptron, which learned this all four. I mean, like, you can visualize that, right? So that is why, after these three folds or three perceptrons, the input space has been divided into eight regions instead of just six. In this case, if you have just three perceptrons, we can divide it into just six regions. But here we could do it into eight different regions. Then what we did was we passed the same output of this third perceptron into the next one as input. So after these four perceptrons, the output would could divide this input space into 16 different regions. So you can identify 16 different classes or regions in this input space. So if you just try to make a table of this, like folds versus regions for both of this. So in the first case, after my first fold, I had two regions. After second fold, I had four regions. After third fold, there were six regions, four, eight, and so on. Like you can observe the pattern after n folds, there are two n regions in the input space. But now, in this second case, after my first fold, I had same two regions. After second, there were four, and after the third fold, there were eight regions instead of six. After the fourth fold, there are 16 regions. So the pattern that you can see here is after n folds, you have 2 power n regions. So this is the reason why this is so incredible. Meaning, if you have a deep network instead of a wider network, with even with lesser number of perceptrons, you can divide the input space into the same number of regions. Or if you want to say it in a different way, you have say n perceptrons. If you stack all of them in same hidden layer, you can divide the input region into some 2n or some order of n times regions. But if you stack them one after the other in different layers, then you can achieve exponential number of regions in the input space. So this shows how powerful deep networks are in comparison to wider networks. So now we'll go back to our presentation and continue. So this was the reason why I took up this illustration here. This gives you an intuitive feel of why the depth of the network matters. So now, did you know that ChatGPT 3 has 96 layers? Meaning, like one after the other, there are 96 layers, and GPT 4.0 has even more than that. Like they've not officially released the numbers, I think. So, but obviously, it has much more layers than GPT 3. Now, just imagine you have just one number input X. So this is that input X, and assume that each layer has just one perceptron. For now, just assume there's just one perceptron in this layer, one perceptron in this layer, one perceptron in this, and so on. You have 96 such perceptrons. Now this output can divide this input space into 2 power 96 regions. uh, just think how incredible this is. Meaning, if I just stack perceptrons one after the other in this, just 96 perceptrons are enough for me to divide this input space into 2 power 96 regions. That is such a huge number. Oh my god. So this shows how powerful these deep networks are. And in reality, GPT-3 it just doesn't have just one perceptron per layer. It has many perceptrons in each layer and many perceptrons in every single layer. So that is why it makes such GPTs and all this so powerful. So now, like, I'll just ask you a quick question. This is simple only. Like, say in this particular diagram that I've shown here, what if you assume that in every layer there are 100 neurons? Every first layer, second layer, every single layer has 100 neurons and 96 such layers. Now, the after the final output, the input space, the statement is input space is divided into 100 into 2 power 96 regions. Is this true or false? You can just put your answer in the chat. Is this true or false? Like the statement is, I just extended this into 100 neurons per layer, 96 layers. So we saw that if you have just one neuron in every layer, then the input space is divided into 2 power 96 regions. So now what if you extend it some 100 times? Now the key thing that you have to note here is that it is a fully connected network, meaning every neuron in every layer is connected to every other neuron in the previous layer. So in this fully connected network, what is the total number of regions? Is it 2 power 100 times 2 power 96? I'll just draw a figure for that, like for you guys to visualize this. So say you have uh, the input to be some number x. Oh, shit, one second. Just one second. Yeah, shit. Why is this not writing? Uh, okay, I don't know why this is not writing for now. So like the question was simple. If you have such a fully connected network with 100 neurons per layer and 96 layers, I said that we can divide the input space into 100 times 2 power 96 regions, and the answer to this is false, because you can divide it into much more than 100 times 2 power 96, because if you just imagine like each of these neurons which are connected in just that those straight lines, you think that there are 100 such things, so 100 times 2 power 96. But in reality, like since it is a fully connected network, you can traverse in any order. Like you have so many different paths to go from input to output, and for each of this path you can have a 2 power 96 regions in the input space. So since it is fully connected, like the order of these neurons don't matter, you put one above and one below, it is still considered as a valid path. So that was what you had to visualize in this. So now going back, so now let's discuss about activation functions, meaning in this earlier slide we discussed that we could extend this notion of output space from discrete classes to continuous outputs by considering such pulse functions and evaluating many of such things. Now let us see a much better way to do this, because the main problem here was that each of our threshold activation function that we used, each of these building blocks or perceptrons were inherently discrete, outputting discrete numbers. And with these discrete numbers, we try to approximate a continuous function. Now, what if instead of output being discrete, we use some continuous output? So that is what we'll try to see now. I don't know why my stylus is not writing. So for now, I'll just show you what I had written yesterday during my practice time. So now say you have this activation function. Now let's first discuss this. So here you had x1 to xn as inputs. This was the basic definition of perceptron that we saw earlier. We had n inputs, and the output y, we said that it is 1, meaning it will fire when the output is, if it fires, it means the output is 1, else it is 0. And when do you think that this is going to fire? The when sigma wixi is greater than equal to threshold was what we discussed. Now, instead of this, what we can do is we can write the same thing, this output y is equal to this, in terms of what is known as step function. I think I discussed this earlier as well. So this kind of function is known as a step function, where the output is 1 when the input is greater than 0, and it is 0 when the input is less than 0. So we can write this particular the output of this perceptron using this step function as y is equal to step of sigma wixi minus this threshold t. Now, how does this help us? So, like, let's try to first visualize what this is doing. So, say you have two inputs x1 and x2. So, you are in this two-dimensional plane, and then the input point is somewhere here. The say that sigma wxi is greater than 2. So the boundary that we have learned is x1 plus x2 is equal to 2. So this is like 1 times x1 plus 1 times x2 with threshold as 2. So if it is greater than 2, say if my point is somewhere here or here, the obviously it is greater than 2, so the output is 1. So in this particular region, the output is 1, and in this particular region, the output is 0. Now, instead of just having this particular jump thing, what if we take a smooth continuous thing for continuous function, or instead of this step function here, step was inherently discrete. So what if we replace this with some other continuous function f, and use this as our model for the perceptron? So this gives us the idea of activation function. So this function over here, which is the continuous analog of what we discussed earlier, is known as an activation function. Here, so basically, like two questions that come to our mind is why do we need an activation function and what activation function do we even choose? So to answer that, so let's assume that what will happen if there's no activation function. So this is logically equivalent to saying that the activation function is equal to this identity function, meaning it is just y is equal to x line. So if there's no activation function, then there comes a serious problem. That is, say if I have my input x, I pass it through one perceptron, and the output that I get is w1 x1 plus b. Then I pass that through another perceptron. Then I get the output of that is I multiply the previous input by w2 and add a term called bias b2. Here there should be one plus b2 as well. And then so then what then after the third perceptron it is w3 times this plus some bias b3. So basically if you see this whole thing can be rewritten as some w times x plus some bias p. So we can combine all this w1 w2 w3 into some number w and all the other remaining things into some constant term. So this the whole three layered model that what this is trying to learn is the same thing that one single perceptron can learn. So it means that I can replace this whole thing with just one single perceptron. So this means that, and we know that a single perceptron is capable of learning some linear boundary, right? So it means that this whole network is learning just one single linear boundary, which we could have learned using just one single perceptron or just one single hidden layer. We didn't have to go deep at all. So the main issue or flaw with using no activation function is that the whole network becomes just a linear function. You cannot express any non-linearity. So everything is linear. Every layer has just a linear. You're just doing some linear transformation on every input in every layer. So the whole point of deep networks becomes irrelevant. And we saw how important deep networks are in the previous demonstration. So in order to make use of the fact of the deep networks being so powerful, we introduce these nonlinear activation functions. So I hope why the question of why activation functions is clear. So now what all activation functions can we use? So generally we use something like this. This is known as a sigmoid activation function, which is given by y is equal to 1 by 1 plus e power minus x. So this is like a smoother version of the threshold step function. Our step function was something like this, but now here we have some smoother function. This diagram is not so neat, but like fine. So this smoother version of the sigmoid activation function is also one thing that we can use. Generally, this is used in case of binary classification where the final output neuron is passed through the sigmoid activation function, so that the output of that can be interpreted as probability of something being, since it is between 0 and 1, we can interpret that as probability of the output being one class or the other. So it is generally used in such cases. We can use it in hidden layers as well. Then we come across another very important activation function called ReLU, which stands for rectified linear unit. It's a very simple one, which is y is equal to x if x is positive and 0 if x is negative, meaning every positive number is retained as such and every negative number is squished to 0. So this is the most widely used activation function and most popular one. And this was what I used in the earlier demonstration of approximating that sign and the other function. I said that I used the ReLU activation function, right? So this was what I used there. And this made the learning process so fast and I could achieve the same. If I had to do that with threshold, I would have had to use more perceptrons than what I required with ReLU. So and then people also use something as this is known as leaky ReLU, where the only change from ReLU is that when the input is negative, it is scaled by some factor alpha, which is some small number like 0.01 or something. So this is another activation function which people use because like here we don't know how far, if we are negative, we don't know if it is -2 or -3. So everything is going to 0. So there are some issues like now where did all of these come from? Like why do we use only these particular activation functions? Like why don't we use some arbitrary, like how did one decide upon all these? So in the end of the session, if I get time, I'll discuss this question. So basically you guys can also ponder over this, like every, like say you start off with threshold activation function, you encounter some problems with that. One major problem that we get is we don't know how far we are from the threshold. Like if the threshold is say 2,
we get the same output for when the sigma wxi is equal to 3, and same thing when we get that equal to 5 as well. Both are mapped to 1. So we don't know how far we are from the threshold, so we're losing some information when we pass it through this threshold activation function. So in order to overcome that, people made a smoother analog of this known as sigmoid activation function. There's another issue with that, that is the gradient is always zero in or not defined for that in case of threshold activation function. So because of which learning becomes very difficult. I won't go into much detail of that. Like after the session, you can probably like explore all these activation functions. Like say start with threshold, find out what are all the drawbacks of that and why is it not so widely used. And when you find out the drawbacks of that, try to think if that is solved using the next one, that is does sigmoid try to solve the issues that this had. Then you will figure out that sigmoid is much better. Then ask a question like, what are the drawbacks of using sigmoid? You get only output bit confined between 0 and 1. And then also there is problem of vanishing gradient, meaning if you go very far from threshold, the gradients become 0. So updation becomes very slow. So like even if you didn't get everything what I said, it's like you can take this as a homework. Like you can do this after the session, explore all these activation functions. So then check if Relu can try to mitigate the problems of sigmoid activation function. Then you will come across some drawbacks with Relu, then go to leaky Relu, and so on. Like and by the end of that exploration thing that you do, you will figure out that it is just a hit and trial. People just found out Relu and just saw that empirically it works, and it works, so people are using it. So that is how they came up with this. And there are some other activation functions as well which are commonly used, uh, like it is shown in this figure. Relu, leaky Relu, tan h, the hyperbolic tangent. There are some others as well which can be used based on a requirement. It's mostly empirical choice that we do before training a network. Here, this middle one, linear, is one thing that we mostly don't use, because if using this is equivalent of not using anything. So when we saw the problems of using linear activation function or no activation function, because it becomes, the whole network becomes a linear map and there's no point of depth. So that is why this is not used mostly. And this is what we have covered till now. So we discussed all these different models and perceptrons, MLPs, how powerful they are, and we even discussed about neural networks, like all these, how to make these the vanilla MLPs much powerful. So now let's one thing that we assumed till now is all these weights and thresholds or biases that we had, we assume that we can learn them by somehow. Like we just assume that they can be learned. If you remember in that quadrilateral thing, I said that you can have one perceptron to learn one of the edge. I said that we can do. So now we'll see how we'll do that in practice. So that leads to how these networks are trained. So before going to this, how networks are trained, I just wanted to introduce some small technical terms, the starting few of which you guys must have already been familiar with by now. So here in this earlier slide of this MNIST handwritten digit classification thing, I said that we can use MLPs to classify handwritten digits, right? So this network is basically trying to do that. It has 784 input vectors and 10 output, 784 input neurons and last 10 output neurons. And this image I took from the famous 3 Blue 1 Brown channel, where he has an awesome, excellent playlist on neural networks. So do check that out after this session. You'll get a full deep understanding of the whole thing. This was just an introductory session. So neurons are basically these dots that you can see here. These are the building blocks of this network. And weights are all the strength of these connections. Like you can see this red and blue lines, right? So this red and these blue lines that you can see here, these are the weights. And these biases are basically the, when you bring the threshold to the other side of the equation, you get negative of threshold, right? That is basically bias. So these biases are also associated with each of these perceptrons or neurons. And here in this entire network, the architecture of this, like how many neurons are there in each hidden layer, this is determined earlier. This is not calculated, this is just fixed. We fix the hidden size dimension to something, and that's also called as an hyperparameter. You can check this out later on. But we call this weights and biases collectively as parameters, because these are the numbers that we can adjust or fine tune in this network during training process. So if we change these weights and biases, or collectively called as parameters, then the whole network function that it is learning will change. It is basically when in this whole, if you assume it as a big function, you're changing the numbers in the function definition. So that is what you're doing by adjusting these parameters. And then this hidden layers are basically, these are the hidden layers, and the architecture is this structure of this network is called as architecture. So I just wanted to introduce these before proceeding further. So now let's get into how these networks are trained. So basically here we have a data set, and the goal here is that I provide this network with some data and I wanted to learn from this data. So what we essentially have is, for some input x, the output is y1. I know this prior. So here x and y are vectors. So meaning I can have any number of neurons in the input and output space. So earlier it was x was a 784 dimensional vector and y was a 10 dimensional vector. So here I have a data set which says that for this input I have this output. So this is what I have in this data set. And similarly, I have a lot of this. I have collected data which says that for x2 the output is y2, for x3 the output is y3, and so on up to some xn, the output is yn. So generally, we have very huge data sets, and the larger the data set is, the more the powerful this network can be trained. So it is basically you're giving the network data or examples and asking it to learn from this the mapping between input to output. So you want to learn which function can map this input to output, so that next time when you give some other arbitrary input, it should give a reasonable output, which is close enough to what you could expect. So this is what we have initially. So we have some network architecture with us, where we decide what are the hidden dimensions and all. And initially the weights and biases, the parameters are randomized. So we start off with some random value, and the goal of this training process is to learn these parameters which will map this particular function. So we use this particular architecture network to learn this from this data set, the function that maps input to output. So now how does this training process work? So first what we do is we take any one of those input samples x1, we pass it through the network, and then we get some prediction y1 hat. Now we know that the ground truth is y1, not y1 hat. So now what? Now we have to, this process of finding out the prediction from the input is known as forward pass, because we were propagating forward in the network. For every input, what are the hidden activations and everything we are calculating, we're going in the forward direction. So this process is known as forward pass. Now what we do is we want to somehow say how good this prediction is. We want to quantify whether this prediction is good or bad. So in our we can sometimes we can just intuitively say, for example, if in a classification task the actual label is one, it is one class, but your prediction said it is zero, then it is obviously very bad. If for one it said 0.5, it is okay. If for one it says 0.9, it is good, something like that. But this is just a qualitative feel that we get. But we need some quantitative measure in order to tell how good or bad this prediction is. So for that, we define another function known as loss function or objective function. And this function tells me how good my prediction is. It tells how close y1 hat is towards y1. So if my loss is smaller or closer to zero, then the predictions are closer to the actual ground truth label. Here these y1, y2 and so on are the ground truth, the reality, and these are the model's predictions. So if the loss is zero, it means that all the predictions are exactly same as the true values. That is the ideal thing that we desire to hope. So now we have some loss function which takes in this prediction and the true label y and tells me how far I am, or how bad this model is or how good it is. So now here the aim of this training is to bring these predictions closer to the true value, right? So the main key thing about this loss function is the predictions come closer to the actual value when the loss function is lower. So this loss function is designed in such a way that as the prediction becomes closer, its value decreases. So now, so the goal of training becomes to reduce this loss function. Now I cannot change the true values. Like I cannot change y. The only thing that I have is this predicted value. So how do I change this predicted value? I can adjust this model. So you can see this predicted value. I got it when I passed this input through this neural network. So it is neural network of X. This you can also think in a different perspective as some function of all the parameters and the input. So now why this theta over here is a representative of all the parameters, like all weights and biases collectively are represented by this symbol theta. So if you assume that this loss function is a function of all the parameters and the input x, then you see that you don't have this y in your control, you don't have x in control. They're all from the data itself. You cannot change the data itself. The only thing that you have in control is this parameters theta. So if I am somehow able to adjust this parameters theta in order to bring loss function closer to zero, then I can expect this predicted values to come closer and closer to the actual values. So this process of adjusting these parameters to bring loss closer to zero is what is known as training the network. So how do we adjust these parameters? How do we achieve this? So let's go much more deep into this. So this is achieved by process known as backward pass, also known as backward propagation. This was one of the learning rules, learning algorithms that we discussed in the first few slides. So which I said is most widely used. So what we do is it's the same thing. First we do forward pass. We take this input, pass through the network, get the predictions, and we already know that y is the ground truth value. Then we calculate the loss from this to be something. Then what we do is we calculate one key term that is known as gradient. So if you've taken any calculus course, you must already know that gradient points in the direction of steepest ascent. Meaning here when I take the gradient of this loss function with respect to each of this parameter, I get the direction in which the loss function increases at the highest rate. So I'll explain this in much more detail in the upcoming slides. So for now, even if you didn't get an intuitive feel of what this is, it's fine. In the next few slides, it will become much more clear. So here, the key thing that we have calculated is this term called gradient. How fast this loss function changes if I update this one particular theta I by some small number. I do this for every parameter, like every single parameter. If I change it by some small amount, how will the loss change? So this is what we calculate. Now, then what we do is, okay, so I know that if I move in the direction of gradient, if I adjust all the parameters in the direction of gradient, then the loss will increase at the highest possible rate. And this is exactly what we don't want. So what we do is we update each of these parameters in the opposite direction of gradient. And that is why we use this negative sign, minus sign here, so as to move in the opposite direction of this gradient. And we also and how much do we move? We move a distance which is proportional to the magnitude of this gradient, and we scale it by some constant factor known as learning rate. You can check about this later on. This tells how fast am I updating these parameters. So now the key takeaway from this slide is, so this is how we did forward pass. Uh, After forward pass, we got the predictions, and we also evaluated the model by calculating the loss. So now I know how bad or good this model is. I want to make this better. So that process is known as backward pass, where we update all the parameters by some factor, by some term known as this proportional to gradient. And by doing so, I expect that if I do a forward pass again with the updated parameters, I expect to get a lower loss. So that is what will happen most of the times, except for one sometimes where we overshoot the minima. So you can check this also afterwards. Like I hope you guys are curious enough to check out all this. Like you can check later on about overshooting the minima. It happens sometimes if the learning rate alpha is too huge. But in most of the cases, what happens is after each of this update, after I update these parameters, if I do a forward pass again on the new set of parameters, I get a lower loss. And lower loss indicates that my model is better than earlier. So it means that if I do this process again and again, like forward pass to calculate the predictions and loss, backward pass to update weights, and again repeat this process again and again, then eventually this loss function becomes so low that it will converge to zero, or it will become very close to zero, and our parameters will converge to some stable value, and that is when we say that we have achieved the best model and we stop the training process. So theoretically, it should take infinite updation steps to reach the minima, but practically we just stop after some iterations. So let's discuss this backward propagation in a bit more detail. In the previous slide, I just took one input sample, like I just took x1 and calculated the loss and used that for calculating gradient. But in reality, we will have a very huge data set. We just if you use this one input, it means that you're making the model to learn that particular map. But instead, we want the model to learn this whole set of data, like whole data set, right? So that's why we take all these input x1 to xn, pass it through the network, calculate all the predicted values, then calculate all give we already know the true values for all of this because that's in our data set. And then what we do is we evaluate this loss function for each of this pair, prediction comma true value, and we take the average of all these loss functions, and it is this average loss that is used for calculating this gradient and this updation step. So by taking this average loss and making it learn this average, try to minimize the average loss, we are essentially telling it to learn learn this entire mapping, the whole function that maps all of these simultaneously. So that is how this model will learn the entire data set. So now let's try to visualize how backpropagation works. This process also has gradient descent because backpropagation is the process of updating weights, and gradient descent is where you tell how much to update each of these parameters. So here the plot that you're seeing in front of you is the plot of loss versus any of those two parameters. So here for visualization's sake, there are just two parameters like some two weights, and the curve that you can see, that curve represents loss as a function of these parameters. So the peak red topmost points over here represent points of very huge loss, and the bottommost point represents the minimum, and this is the region where we want to reach. So if we reach this point of minimum loss, this is the best model that we can ever achieve. So this was the step that we discussed earlier, that is we update each of this parameter by this term proportional to the gradient. Here they've used loss, they've represented loss with the term j, but that's the same thing. And this point over here is our target. We want to reach this particular target after this model has been trained. So what we do is first we initially start off with some random position. So I said that we initially randomize the weights and biases, right? So when we start with a random value, this model is like almost arbitrarily guessing some predictions. It doesn't know anything about the data set yet. So this arbitrary model will have very huge loss because that doesn't know anything in a data set. So when we try to find the loss from average loss for all this model, it will be usually very large value. So our goal in this gradient descent is to reach this minima starting from here. So what we do is after iterations, say after 10 iterations, we reach some point here. So now what we are doing essentially is at every point in that gradient, this loss function curve, we calculate gradient, which tells in which direction to move to increase the loss at the highest rate. Then we move a small distance in the opposite direction. Then from that point, I again do forward pass, calculate loss, then again calculate gradient, then again go a small direction in the opposite direction to gradient, and so on. I do this again and again, and you can see that we are moving on this curve, and the path that we are following would eventually lead us to the minima is what we expect. So then say after some 10 iterations we reach some point here, and eventually after say some 1000 iterations we come somewhere very close to minima. So and after that point we can like stop the training process and say that this particular model is the best one because it has the least loss of all what I've trained till now. So, the moral of the story or the essence that you have to learn from this is that loss function will tell what to learn from data, because we have to adjust this loss, we have to decide this loss function in such a way that when the predictions are close to the actual values, the loss function should be very minimum. So, loss function is what determines the shape of this curve. So it is telling me what to learn. It is telling me where the minima is. But gradient descent is the one that is telling how to learn from this data. If I start from some random guessing model, how do I update? How do I teach this that if you update the parameters in this fashion, you will decrease the loss, meaning you are learning the data set. So that is what gradient descent tells us. So let's go over one quick example to illustrate this, and I think it will be very clear after this example. So this problem that you can see here is also has linear regression, where we are trying to find the line of best fit which passes through all, which it's not like passing, it tries to approximate this all these data points here. So it's like a linear interpolation between all this. So here we want to find out the best fit line. So how do we quantify which is best or which is good or bad? So that is where loss function comes into picture. And in this particular task, the most widely used loss function is known as mean square error loss. It is basically you calculate the error in each time by taking the difference of the prediction from the two value, square that, and take the average of that. So it is basically the mean of the square of the errors. So that is what is known as mean square error loss, and we try to minimize this mean square error loss. So let's try to visualize how this mean square error plot looks like. So if you have some, say if you have just two inputs, in this case I have just one input x and the output y. If you have some another input y as well, in this case the loss function will look like this parabola, as you can see here, with zero loss when the this is just to show that it's parabolic in nature. So when the weights are in such a way that we get the best fit line or minimum loss, that is where we have this minima of this parabola. And if we extend this to higher dimensions, say if we have two inputs, then it will be like a paraboloid, and similar things in higher dimensions as well. So we initially, when I meant that we start off with some random parameters, I mean that initially the line is some random line. It can be anywhere. That time it will have very huge loss because it doesn't know where the data points are. But eventually, after training, it becomes closer and closer and closer and closer, and finally come uh, as close as possible to this best fit line. So this is gradient descent in a nutshell. So here, say if this is my cost as a function of some weight, they have considered for now you just take the cross section as with respect to one particular weight. Here, gradient in this case is just the slope of that. So when your slope is positive, it means that if you move in the positive direction, if the weight changes in positive direction, then the cost will increase. So what we do is, if the slope is positive, we move in the negative direction so as to decrease this loss. And we do this again and again. Here, the as you can see, as we go closer and closer to minima, the gradient slope becomes closer and closer to zero, right? So as slope becomes closer to zero, our updation step, meaning we update it by some scalar times the gradient, right? So that scalar times that slope becomes closer and closer to zero. So initially I start off by moving taking large update steps. Then as I proceed in this training, the step size becomes smaller and smaller, and this ensures that eventually after some large number of steps, I will converge at this minima. I won't go in the opposite direction again. Like after this minima, I'll not again overshoot it. So sometimes that happens when we have very large learning rates. So you can check that out in the later on after this session. So now I want you guys to answer one quick question. So like in calculus courses, we generally study that if we want to find the extremum points like maximum or minima, we calculate gradient and we equate that gradient to zero, and we say that that point is either a maximum or a minima. Then we do some second derivative test or something to tell whether it is either a minima or a maximum. So why don't we do the same thing here? Like, why do we think we are taking this convoluted step of moving along this loss function, like taking some thousand steps, moving one after the other? Thousand is just a number, but some large number is what I meant. Like, why do we do forward pass, calculate loss, then update, then again do the same thing again and again? Why do we do it iteratively is my question. So do you guys have any thoughts on this? Okay, Gautam says that we don't know the function, right? We know each of this activation function, right? So can you elaborate? I think you're very close to the actual answer. So can you just unmute and tell?
Yeah, so like you said about the method where you set gradient to zero, right? So like in those you have
Huh.
the function exactly like x square plus y cube plus xy equal to something. Like
Huh.
we have that function and then we differentiate and then we set it to zero, right? But here we don't have that explicit function, right? Because it's an unknown data set.
Yeah. So that's the correct answer. So the main answer here is that we don't know the exact function which we are trying to approximate to take a gradient. Yes, so the main thing is there we had that analytical form of that function. We had the equation of that function. Here we don't have that analytical form, and since there we had that analytical form, we could take gradients, and the gradient that we calculated was an expression. Like it was expressed in terms of all the weights and parameters, and that if you set it to zero, you can calculate. But here, the gradient that we calculate is not an expression, it is a number. We evaluate this gradient using methods like chain rule, which you can see later on. In chain rule, we just calculate the gradient as a number. We don't get gradient as an expression so as to equate it to zero. So and even if we can try to write analytical form that becomes very large. Like if you have some 100 neurons and each of them, you know that it's some sigmoid. If you use some sigmoid activation function, you know some w1 times sigmoid of something something, it becomes so large that it's practically impossible to write such a big thing in paper and calculate the analytical form of gradient. And that is not even efficient, as you have to do this for every model architecture and that becomes a mess. So the inexistence of an analytical form of this thing makes us use such numerical methods to find out minima. Here this iterative process of finding the minima is a numerical method. It is not like a pen paper work. We have to it's very difficult to do in pen and paper. We have to implement it in some GPU or something. So this was an interesting question, and good that Rishita and Gautam got the answer for this. So now comes the this session has come to a conclusion stage. So now we went over all this, like we saw how people try to approach how human brain works by discussing some early models, and then we saw went over connectionist models, and then we saw about perceptrons. And by now you would have got a very amazing feel of what perceptrons are. How can we be sure whether it's local minima or global? That depends on the nature of your loss function, because like generally if you have this, in case of linear regression, you have this parabolic loss function, right? So there exists only one minima. In that case, you can be sure that you will, if you have reached the minima, it means that is the only global minima. But in case of several different if you have several minima, some are local, some and only one is global, in that case gradient descent will take you to the local minima only, because it depends on where you start. Like wait, I'll show you in the previous slide. It's a very nice question, because like in this, oh shit, once again, if you see in this loss function curve, here there are, you can see that there are two minima, one this blue one in the front and blue one in the back, right? So since I started off initially at somewhere in the front region, that is the reason why I followed a trajectory which led me to the front one. But I still don't know whether that is global or local. So the naive gradient descent that we discussed now will lead us always towards some local minima. If I had started off with some other random initialization, if I start off somewhere else in this weight space, then I may reach some other local minima as well. So we cannot be sure whether it's local minima or global minima. So if you have enough compute, then what one method that you can do is you start off with lot of initializations. So like you take one initialization, a random thing, train that model up to some iterations, check what is the loss after that, then start with some other initialization, train that and check the loss. So that is how you can compare which of them is global. So it's difficult to converge only at the local minimum. There are other variants of gradient descent as well, like people use some different optimizers and slight modifications to this, so that even if it reaches some local minima, here what it will do, it will converge there. Like it won't, the updation step becomes smaller and smaller, it will converge. But people try to make variants of this whereby even if you reach a local minima, it will again overshoot and it will not converge till you reach global minima. So there are different methods for that as well, but the thing that we discuss now will lead you only to local minima. Are there methods to converge to global minima always? So as I said, like you can modify this gradient descent algorithm, that updation step, by using several optimizers or some other methods, by which even if you reach a local minima, if you feel that if it feels that it's a local minima, not the global one, it will not converge. It will again overshoot, and it will eventually converge at the global minima. So I hope that is clear. Nice doubt, by the way. And so then by now you would have got an amazing feel of perceptrons, MLPs, you get a feel of why ChatGPT is so powerful. When I first saw the results of ChatGPT, it was literally a magic. It's like, how is it even capable of doing it? But now I hope that magic has reduced for you guys as well. So now I'll just show some small things to tell you like what all are the recent advancements in this mathematical modeling in the same journey if we continue further. So there is one type of model known as autoencoders where we use such fully connected networks to reduce the input space to something known as a latent space or latent dimension distribution, and from that we try to reconstruct the original input. So this is an interesting thing where this is used in many generative AI models. Like it is used for generating images and many such applications. Autoencoders are used, so you can, if you are curious enough, you can look up after this session. Then also in 2017, there came up this paper, Attention is All You Need, where they introduced transformer architecture. And here the most important key thing in this transformer architecture is this was meant for modeling sequence to sequence tasks. So like some text you want to generate the next text word or something. So here also they use multi-layer perceptrons. You can see this MLPs here in both this encoder and decoder. I won't go into the depth of all this because it is beyond the scope of this session, so you can take a look at that paper as well after this session. Now I'll give you a glimpse of how ChatGPT works behind the scenes. So basically, the figure that you are seeing here is of a smaller version. It's called Nano GPT. This is the entire structure of this. These rectangular boxes that you can see represents the weight matrices. This is the close-up view of that. All these rectangular matrices that boxes that you can see are uh, weight matrices which are used for carrying out large MLP forward pass. Like we had so many weights, so many biases, right? So an efficient way to do forward pass is to stack all of them in a matrix and do matrix multiplication. Because when we do matrix multiplication in a GPU, it becomes much more efficient because of parallel computation. So, and as a fun fact, like in ChatGPT, more than two-thirds of its, like in transformer, is mainly made up of two things. One is attention heads and this MLP layers. So approx some two-thirds of its parameters lie in these MLP layers. Only some a fraction, one third of it or something is residing in this attention heads. So it is this. There's also a nice analogy. Like these attention heads will learn the language, and this MLP learns the knowledge of this world. I don't know if you guys got that. Even if you didn't get it, it's fine. So we require so many numbers in order to learn the entire world knowledge. That is why two-thirds of ChatGPT's parameters lie in these MLP layers. So hope you got to know how powerful these MLPs are or neural networks are. So these are some of the references that I used and which you can see later on after this session as well. These are some of the main topics that you can ponder over, like when to use a specific activation function, what is the effect of learning rate, should it be too large, too low, overfitting and underfitting. You also come across a term called as bias variance trade-off. Then chain rule is one amazing thing of, like, it's used extensively in finding out these gradients. Even when you don't know the analytical form, how do you numerically calculate the gradient? That is using chain rule. So it's a very useful thing. So then comes regularization, and you can even check that out as well. So thank you very much. So just before leaving the session, just put your attendance in the chat, and I hope this figure makes more sense for you all now. hope you guys enjoyed this session. So thank you very much.